Let us start with embedding of graph nodes. Okay, so we have an undirected graph G, okay, V. The adjacency matrix is A, and we want to compute an embedding, okay, which is represented as a vector with the embedding of length K for every node V, and with the node by small z of V, the embedding of the node V. Okay, and we consider graphs without node features, which means that we are essentially building an embedding out of the graph structure itself, nothing in addition to the graph. If you want to incorporate additional features that you got from the data, you combine it somehow with these features. Right now, we're looking at just embedding just based on the graph structure. Okay, what do you do with these embeddings? So one thing is that you can learn a model over the nodes using the embedding as the features, and we're going to see some results. That's called a downstream task. Okay, the prediction over V is a function over the embedding of V. Okay, similarly, you can do it for link prediction. The prediction over the link UV is a function of the embedding of U, comma, the embedding of Z, of AV. You can do clustering by clustering numerical vectors. Okay, that gives you a clustering of the nodes. You can do visualization like t-SNE. Uh, we'll see more examples in this part. Some techniques use the node embeddings to actually come up with an embedding of the entire graph. For example, in molecule embedding, you can take a sum or an average of the individual embeddings of the nodes. Okay, so that's another use. Okay, principal technique is, or principal technique for embedding is self-supervision. What is the idea of self-supervision? You basically produce examples, labeled examples from the data itself. You don't use any external process or human in the loop or anything like that. The data itself is used for automatically producing labeled data. Okay, so you essentially produce a task from the data itself, and this task is called a pretext task. Okay, and then with this task at hand, pretext task, you learn a parameterized model, which includes the embedding that you want to optimize. And but this is a general technique, the self supervision. Okay, but yeah, used for representation learning. So two ideas or two techniques for self supervision are masking and autoencoding. Okay, in masking, you basically take your input. Here it's a figure, it's an image, and you hide some part, mask some part. And your task is to reconstruct, okay, unmask what you've hidden. Okay, and if you're doing a good job, then you should be able to properly unmask. But you know what is what is your objective. So here you see it's not exactly the same cat because this part is different, and you do the best. This is an optimization problem. Okay. The idea of autoencoding is that you take your input, you encode it in some way. And this is relevant to us because this is going to be our embedding. Uh, and think of some low degree embedding with some normalization and so on. From this embedding, you want to reconstruct what you started from. Okay, so here we reconstructed the cat, and there are some mistakes and so on. Um, but if you're able to reconstruct, then it means that you have a good embedding, good low degree representation. Okay, so that's the idea. You want to be good at reconstruction, so you should get an embedding or representation that is a good representation of your input data. Okay, and this is what we're going to use. Specifically, we're going to look at embeddings through the encoder decoder paradigm. Okay, so what is the idea? We have a pair of nodes, okay, and we essentially encode them through these embeddings, through these vectors. What are we encoding? Well, we encode a similarity between the nodes. We have some notion of a similarity, and we encoding instead of writing the number, we say, okay, this is a representation of the blue node, this is a representation of the green node, that's your representation. Okay. What do we do with that? Well, now we want to decode it. We want to take these representations and apply some decoder and reconstruct the similarity. Okay, we would like so we basically produce a number which we want to be similar or close to the original similarity measure. Now it's important that this is a simple decoder, right? We do not want this embedding to be too sophisticated and essentially leak the information that you have originally in the graph. Okay, so it's important that you use a simple decoder, and so the responsibility of being good is actually on the embedding. The embedding should be good, and if these are good embeddings, you should be able to reconstruct the measure. That's the idea. Okay. Now, basically, what the encoder is doing is producing the embedding. That's going to be our embedding technique. And then the question is, what is the decoder that you're using? Well, first, what is the similarity measure that you're using? Then, what is the decoder? And how do you measure the difference between the original proximity and the decoded proximity? That's all. Okay, so put it in more formal terms. We want to learn this embedding Z. We define three components: the proximity function P, taking two nodes and producing a number; a decoder function, taking the embeddings of length K of two nodes and producing a number. And we want this number to be close to P. So we have a loss function that takes these two numbers of P and D and returns a number. This is the loss, how much we are losing, how far the two nodes are from each other, and that defines the cost. Okay, the cost of an embedding Z is taken as the sum over all of the pairs, UV, of the loss between the actual proximity by P and the decoded proximity D of the embedding of U, comma the embedding of Z, of AV. Okay, and the goal is to find a Z with a minimum cost, a Z that minimizes this function. Okay, now this is basically template, right? And you can instantiate this template by using different combinations of D, P, and L. And actually, you can see in the Hamilton book, there's a reference in the course website, showing how basically different techniques that have been proposed in the past are essentially different instantiations of this framework using different combinations of D, P, and L. Okay, and we're going to look at several of these in this part of the module. Okay, uh, one uh, repeated issue is that of scale, practical issue. And this is basically, the issue of how demanding this function of the cost is. There are two issues of scale here. First, the cost requires going over every pair of nodes. Okay, and you say, okay, if I'm optimizing using SGD, then I'm taking one pair at a time. If I'm using a batch, and I'm using a set of nodes at a time. But if you want your epoch to cover your pairs, then you have a lot of pairs to cover. That becomes intractable very quickly. Okay, and there's another issue. This decoder function is often required to be normalized. maybe across the U's or across the V's. And so to compute this D, you often need to consider every possible ZU or every possible ZV. And that is something that you do in every iteration of SGD. That's a lot. That becomes infeasible very quickly. And there's a trick that is commonly, repeatedly used to accommodate this difficulty. And this is the idea of negative sampling. The point is that in common instantiations, the set of pairs of nodes for which the proximity is non-zero is small. For most pairs, the proximity is zero. For a few, it is it is non-zero. These cases of non-zero, okay, this sparse setting, these are called the positive pairs. And we denote these pairs as pairs pos. What about the negative pairs, the pairs for which this proximity is zero? So this is all of the rest. And instead of using all of them, we sample a set. That's the idea of negative sampling, coming from Google's Word2Vec. And we're going to see this algorithm later in more detail. But that's the idea. Instead of looking at every pair of negative point or every pair of nodes with proximity zero, we sample a set of nodes that we call negative pairs. Okay? And so the distribution can either be uniform, it is often uniform, it can also be biased, for example, by node degrees. You can see different instantiations of that in different paradigms or in different proposals. Okay? So how do we use negative sampling? First, for the cost, we'll typically use some IID set of pairs, okay? And so what we will have is the sum of positive pairs. We compute the loss as originally defined. Plus, going over this uniformly distributed pairs, we compute the loss. And see here it is basically the value zero because the proximity is zero, and we use D over ZU and ZV. Okay, and we also multiply it by this lambda because it is just a sample. So we want to accommodate the fact that we're looking at just a subset of the node. So we scale it by this lambda. Okay, so that's regarding the cost. For D, we do the same thing. Instead of normalizing over all of the U's, we just sample over some of the U's, U primes, okay, which we sample. Okay, and then this is called the leftward negative sampling. Or if you want to normalize based on the V's, then we normalize based on several or sampled V primes. Okay, and this is called rightward negative sampling. Okay, so this is the idea. Basically, instead of computing this cost function by considering every pair or by normalizing by every node, we just use a set of negative samples for the task. Okay, here are some examples. Graph factorization. This is a work coming from Google. Their focus is on scale. They show, okay, with distributed computing, we can do a lot, 200 million nodes and 10 billion edges. But in terms of the semantics of what they do, it's basically quite a direct instantiation. The proximity is the adjacency. Okay, if two nodes are neighbors, then it is one, otherwise it is zero. The decoder is the dot product. Okay, so the ZU dot product with ZV. Okay, and the loss function is square error. Okay, you take the difference between the numbers squared. And they also use a regularization that essentially encourages the function to use, or the embedding to use small numbers. Okay? Um, so this is the idea, graph factorization. Another one is line. Okay, large scale information network embedding. And they use two notions of proximity, and they also assume that every node has weight. Oh, sorry, every pair of nodes, U and V, have a weight, so the edges are weighted, and they assume that this behaves like a distribution. Okay, the sum of all of the weights is one, so it is normalized. And it's important that this is a distribution. Why so? So the proximity is going to be this weight. Okay, that's very simple. The last function is going to be to say, basically, let's look at, well, we look at this P as a distribution. Let's look at D as a distribution and compute proximity between two distributions like KL divergence. Okay, and this is the term that you would use in the KL divergence between two distributions. The first issue, or minus the first distribution, log of the second distribution, or the second probability. Okay. Now, for decoding, they use two decoder functions. One is sigmoid over the dot product. Okay, so not the dot product directly, but basically some number between 0 and 1, the sigmoid of this number. Okay, and we'll revisit this function later in the course, but it is the exponent is in the denominator and also using a minus. So if they have a high uh, dot product, then this number is higher. Okay, and another one is the exponent of the dot product normalized by this exponent over different u primes. Okay, so you normalize this exponent a function by the different u primes. Okay, so how do they use that? How do they normalize this decoder? Well, basically with negative sampling, leftward negative sampling. They also suggest or propose or develop some improvement of stochastic gradient descent for their loss optimization. Okay, so they show the merit, the value of their technique of the line algorithm using experiments. In these experiments, they do classification, multi-class classification, on page classification of Wikipedia. And they compare it to different embedding techniques like graph factorization. And basically what they do is, like we discussed in the beginning of this part, downstream task. You take the embedding, you train a model over this embedding and test it. And here they use 10% for training, 20% for training, and so on. And these are the different techniques. And the one that works best for them is a line with not just the first or the second order decoder, but actually a combination of them. So that's one way where they show the goodness of their embedding. The other one is the TISN, and this is kind of a case study. But basically, they say, okay, here we have a network. The nodes are authors. We look at three classes of authors based on their domain or expertise: data mining, machine learning, computer vision. Okay, red, green, and blue. And so, look, we use graph factorization, and we don't see any correlation between the types or the expertise of these authors and the the position of the dots in the 2D. So no semantic correlation. With deep work, we see a better correlation. See, there is a green region, blue region, red region. However, there is this condensed part here where many or even most of the embeddings fall into, which is not, a nice behavior. You would like to have some um, uniformity. And then they say, okay, line behaves very well because first the embeddings are spread all over. And you can see clearly that there's the red region, the blue region, and the green region. So that's their way of, providing evidence that these embeddings behave well semantically. Okay, so these are ways of showing that the embeddings are useful. Next, we're going to see other techniques to basically instantiate the encoder-decoder diagrams.